Good morning, everybody, and welcome to the morning session. We start with a short announcement. Well, I don't need it. Okay, so. It was quite strong, but for Florentine standard, quite weak for Italian ones. Anyway, don't panic. I mean, in a way, so it was. Don't panic if Florence is not there. So just tell you better when you have I would like to remind you the world of creativity as I said it, and also to say that GGI is organizing a series this start of the COVID. So we were online colloquia, and there will be one online colloquia tomorrow at 5 at GGI, but actually it will be recorded here. So everybody is welcome to participate. The colloquium will be given by Thomas Frozen on from the field of physics. And start at 5 and it is general, I mean, it's not specialized. So we are all welcome. All right, thank you very much. And we start with a talk by Pavel Bleher from the University-Purdue University, and he will speak about topological expansion and phase diagram in ensembles of random matrices with complex potentials. Thank you.
Okay, thank you for introduction. You can hear me. Yeah. Right, thank you for inviting me in the committee, and especially Filippo, and give me a chance to give this talk. So I will talk about my ongoing project with several people: Alfredo Diani, Maxim Yatselev, Ahmad Barhumik, Ken McLaughlin, and Rusbeh Garhlum. Okay. Okay. Does it work? Okay. So we begin with a brief review of topological expansion in unitary ensembles of random matrices. It's okay? Too strong? Okay. Right. Okay, so let's consider a. Okay, it's too much. Okay. Okay. So yeah, it's right here. We consider first a real polynomial V of some degree D, and D is even, and the leading coefficient is positive. Right, and now we consider unitary ensemble of random matrices, and it's a probability distribution on the space of Hermitian n by n matrices, right? And it's absolutely continuous with respect to the Lebesgue measure, dm, and it has some weight. And the weight is exponent minus n trace of polynomial V of matrix M. Right, and then we have, as usual in statistical physics, we normalize it by partition function. Okay. Say again? No. Okay. Right, and as an example, let me consider the quartic polynomial with parameter u. U is just T4. And the partition function is this, right, matrix integral. And when u equals 0, we are back to Gaussian unitary ensemble. And for Gaussian unitary ensemble, the entries are independent, and the partition function is explicit. Okay. So now it's convenient in what follows to consider normalized partition function. We normalize it by dividing by Gaussian. Zn of u divided by Zn of 0. So now let us make a change of variables, factor m times square root of m. It's m prime, and then return back to m, and then we'll get this integral. So on the top, we have this quartic integral. On the bottom, it's quadratic, right? And so the relative partition function is just mathematical expectation of quartic term. Right. And so now we expand to go to this topological expansion. We expand the exponent of the quartic term into Taylor series, and we evaluate this mathematical expansion term by term. Right. Now, in the Gaussian ensemble, the entries are independent, and this allows us to calculate term by term, right? Right. These mathematical expectations, which are called EP. It is trace m to the fourth to power p. Okay, right. And so let us start with just trace m to the fourth when p equal 1, and this is the sum. And now it's a fourth moment, a sum of fourth moments, and it can be easily calculated by Wick theorem, which tells us that we have to consider different pairings, pairings of these four terms, right? And these are three options. How can we pair? 1 to 2, 1 to 3, 1 to 4. Right. And then this would be the first term, second term, and third term. The difference is here. In the first term, we have just delta function of ik. In the second, we have 3 delta functions, and in the fourth, we have 1 delta function. Right. And because here we have only 1 delta function, it gives us n cubed terms, because it is a 4-fold sum. In the second term, we have 3 delta functions, and so we give effect of n. And here again, n cubed. So the E1 is just 2n cubed plus n. Right. And so this can be represented by Feynman diagrams. So this is the first term, second term, and third term. And topologically, there is some difference between first term and second term. Namely, this can be arranged on the plane or on the sphere without self-intersections. But second cannot be arranged on the sphere, but it can be arranged on the torus. Right, and here it's again on the sphere. And so this is very much related to, right, to counting the number of diagrams. Namely, we have n cube and n cube, and this n cube is counted in the following way: just number of faces of the graphs on the sphere. So the graph is plotted on the sphere, and we count how many faces are there. And this is exactly 3. Now for the second term, we have a diagram on the torus, and there are exactly 1 face. And so E1 can be written as sum over Feynman graphs n to power f of p of pi, where f of pi is the number of faces. Okay, this is the first step. Now with E2, calculations are similar, but we have longer terms with 8 factors. But again, we use Wick theorem, and we partition different ways into pairs. And there are 2 types of graphs. One of them are connected, and one type are disconnected. Okay, right. And so here, pi 0 is disconnected graphs. There are 2 graphs with 1 vertex. And then there are connected graphs where two vertices are connected, right? And so E2 is the sum of two terms. The first term is just E1 square because they're disconnected one vertex terms, and then connected sum. I will go to this. I will go to this. You'll see, right? And so these are connected Feynman graphs of degree 4. So we consider graphs, regular graphs of degree 4, which means that from every vertex there are exactly 4 edges emanating, right? And right, and so this is a planar graph, and this is a graph of genus 1 on the torus, right? And all graphs with two vertices are either connected graphs, either planar or toroidal. Okay, right. And so this can be extended to high moments, and the high moment connected part is sum of n to power f of pi, where f of pi is the number of faces of this graph on the appropriate Riemannian surface. So for each graph, we look at the smallest possible genus. Okay, right. So now we go to a partition function, logarithm of partition function, which is free energy. And this is normalized free energy. And then by the second week here, we have only sum over only connected diagrams, is what I mentioned, right? And so the partition function, if we connect combined terms with n, would be the factor will be f of pi minus p. Okay, and now we apply the Euler characteristic formula. Because this irregular graph, the number of of degree 4, the number of edges is just 2p. And so when we take vertices minus edges plus faces, it is 2 minus 2j, but L is 2p, and so we'll get f minus p equal to minus 2j. And then we substitute this formula 2 minus 2j in our power expression, and we'll get fn of u equal the sum over p, and then sum over all connected graphs n minus 2j. Right. And so what's remarkable here that different Riemannian surfaces of different genus geni are separated. They produce different powers of n. Okay, right. And so fn of u is the sum. Now we change the order of summation, and we'll get a right asymptotic series. When we change the order, it becomes asymptotic series 1 over n to power 2g, and then some functions of u. Right, and this is called topological expansion because it is a summation over genus. Right, and here we have some functions, and if we expand them into power in the Taylor series in U, we will count the number of connected regular Feynman diagrams of degree 4 with p vertices. Okay, and so these are basically generating function for this combinatorial problem, how to count the number of graphs on the Feynman graphs on the Riemannian surface of genus G. Okay, yes, please. Yeah, I didn't need those conversions, right? Yeah. Right. Okay, and now the idea is the following, that there is another way, analytic way to calculate FNFU asymptotics. And if we compare this with this formula, this will give us a solution to this combinatorial problem of counting Feynman graphs with p vertices on Riemannian surface of given genus. Okay, right. And this is usually, I mean, the Feynman diagrams are used as in perturbation theory, in quantum field theory. But here they're used to count the number of diagrams. Okay. Right. So, right. So we have asymptotic expansions of free energy in powers 1 over n square. And the coefficients, functions of U, and the generating function for the number of connected regular Feynman graphs of degree 4. Okay. Right. So this topological expansion has a very rich and big history. It goes back to classical works of Het-Hooft, Brezanec, Parisi, Bleher, and many other people. Right, it's in physics. And then there are many papers now in mathematics as well, proving these formulas. Right. And I will, so one of the mathematical tools to calculate and to prove many results in this area is based on the Riemann-Hilbert approach. And I will discuss it now. Right, but to apply this Riemann-Hilbert approach, the first step is to consider ensemble of eigenvalues of matrix M, and the ensemble of eigenvalues is this Coulomb gas. Right. And then, right, and then the same partition, the same free energy can be written as 1 over n square logarithm of normalized partition function, but now it's partition function of eigenvalues. Right. Okay. Yeah, the only thing I replace here U by 4, but it doesn't matter. It just some formulas I simply a little bit. Okay. Right. And now the partition function of ensemble of eigenvalues can be expressed in terms of the associated orthogonal polynomials. It's known for many years in the theory of orthogonal polynomials, but also in it is expressions for Hankel determinants, right? And it's very useful here. Okay. Right, and so it goes in the following way. So let us consider orthogonal polynomials on the line. I denote this Pn of x, right, and they're monic, so the leading coefficient is 1. And this is the weight. This is the same weight as in our function, basically, right? This quartic weight. And then we have this normalizing constant Hn, which is just L2 norm of Pn with this weight. Right, and this polynomial satisfies the free term recurrence relation, which is very general in the theory of orthogonal polynomials. But in addition, it satisfies the string equation, nonlinear string equation, which gives a relation, nonlinear relation for recurrence coefficients In. Okay, yeah, this is an even weight, and so this free term recurrence relation is in fact 2 term, because the middle term, the midterm is 0. Okay, now we're interested in the end of the day, we're interested in asymptotic of Zn, partition function. And partition function is has this explicit expression in terms of normalizing constants. Right, so Hn is just normalizing constant. Now the partition function, or it's the same as determinant, is n factorial times this product. But what we need, what we'd like to in the end, to evaluate asymptotics of Zn. Now the idea is the following: we will be able to evaluate asymptotics of Hn But unfortunately, in this formula, it involves all terms from n equals 0, 1, and so on. And so for small n, it doesn't work, the asymptotic. So we need to do something else. And we use a different approach based on asymptotics for recurrence coefficients and some what's called deformation equations for free energy. I will explain. Right. Okay. So what is the Riemann-Hilbert approach? Is very powerful analytic approach. It is also called nonlinear steepest descent method, and it is applied to various integrable system, but also to orthogonal polynomials, which is also right. And in some sense, it's also an integrable system. There is Lax pair and so on, right? All ingredients, right? And by using this nonlinear steepest descent method or Riemann-Hilbert approach, what we can do, we can evaluate asymptotics of recurrence coefficients In. Let me show you again. So, right, so this is our recurrence coefficient, and it has parameter n small, but also we have parameter n capital. And so what we're looking for, we're looking at asymptotics of these recurrence coefficients In when n small goes to infinity and n capital to infinity. So both parameters go to infinity, but with some relations between them. They should be of the same order. Okay. Right. Right. And so we assume that they're of the same order, and so n small over n capital is some eta which is close to 1. It can be not exactly 1, but it's not far. Right. And so by using this Riemann-Hilbert approach, what we can do, we can prove uniform asymptotic expansion of recurrence coefficients. And now they're functions of two variables, eta, which is n small over n capital, and u. And then we're interested when eta is close to 1 and u is 0, because we would like to consider Taylor expansion of all functions at u equals 0. Right. And so from Riemann-Hilbert approach, we get that this asymptotic expansion, uniform asymptotic expansion, and right in some neighborhood of this point. And we get also that these are some analytic functions of parameters. But now we can go, we of course we're interested in calculating these coefficients, right? And so what we can do, we take this asymptotic expansion and we substitute into string equation, right? And so now in the 0 order, we get this equation just for R0, the starting term, and this is the equation. We solve it, and we'll get R0. Now, for subsequent high order coefficients, we calculate them recursively by using this equation, this recursive equation. Right, and we'll get R1, R2, and so on. But expressions becomes more and more complicated, of course. Right, and so in this way, we'll get topological expansion, 1 over n square expansion for recurrence coefficients. But now we have to go back. Yes, please. In simplest case, yes. Yeah. Right. No, you're absolutely right. Yeah. Right. Okay. So now, now we have we would like to use this asymptotic expansion of In to calculate Fn. And there is a very nice expression of it's called deformation equation. It is derivative of Fn with respect to u. and it's expressed in terms of IN. And what's extremely important here is that all the big parameter, big index here appears n and n minus 1 and n plus 1. And for these indices, we already know asymptotic expansion. And in this way, we'll get fn prime, and then we integrate, and we'll get asymptotic expansion of fn, right? And so what we get is asymptotic expansion of fn, and this is f0, f1, f2, and so on. These are, but of course we don't have for f3. It's already very big formula. F4 is, and we don't have a closed formula for right for fn for f. Yeah, exactly. Right. Right. Okay. So. Okay. I did something wrong. Okay. Okay. Right. Okay. So now I'm back. Right. And so now we have compare this with Feynman diagram expansion, and we get term by term these coefficients HGP, which is the number of four valent Feynman diagrams with p vertices. Okay. In some sense, we solve the problem, but of course the expressions when g equals 0, it is not very complicated because it's just f0, right? And if you take the J term, it gives us the number of diagrams on the sphere. Here it is number of diagrams on the torus, right, on genus 2 and so on. Right, but now when G is greater than 2, then the formulas are complicated. But we're interested in large p asymptotics of these numbers, AGP. Because how it's applied, I mean, so we consider some Riemann surface and the graphs with a big number of p. Right, because this is approximation to quantum gravity, and these Feynman graphs, they approximate the curvature. Right. And so we're interested in asymptotics of these coefficients, and that's what we find that we prove that it is p to this power 5g minus 7 divided by UC, it's some critical value, minus 112. This is what exactly on the end. Right? Okay. And then there are some coefficients. CJ. Right. And these constants CG are related mysteriously to some special solutions called Boutroux Triton-K solution of the Penlever-1 equation. So let me formulate this explicitly. So consider the Penlever-1 equation. It's written here, right? And we consider this special what's called Triton-K solution. It's some solution of this equation, and we make this change of variables, some scaling appropriate. And then as x goes to infinity, it admits the asymptotic expansion in powers of x. Okay, right. In fact, it is analytic in some sector, and that's why it's called Triton-K solution. It's a big sector, then it's Triton-K solution. Right. And so we have these coefficients of this asymptotic expansion at infinity, right? And mysteriously, the coefficients in topological expansions are exactly these coefficients yg. Okay, right. And so now, how can we understand asymptotics of Taylor coefficients? Of course, we have to go to complex plane. Right, and this is very natural idea which goes back to Francois David in physics. Right, and so we consider this partition function, but now for complex values of u. Originally those real values, u greater than 0. Now this integral is well defined for in the right half plane, but it diverges when a real part is negative, and so we have to regularize this. Right. To regularize, there are two ways, more or less equivalent. One way is to rotate the contour of integration. Here it's real line, but when we change u, we can adjust the contour of integration by rotating it. Right, but slightly more convenient is to make a change of variables, and it's described in the following way. So we change zeta. This new variable u to power 1/4 z, and this is a new variable sigma instead of u, right? And then the polynomial becomes zeta to power 4 plus quadratic term. And now the advantage is that now it converges for all sigma, because the leading term is coefficient 1/4, right? And so the partition function, new partition function, is this integral. Right, and it's trivially related to the original one as functional u, so basically it's the same. Right, and so what I want to talk now. Okay, I'm sorry, it's jumped. Yeah, it is my joint work with Ken McLaughlin and Rusvir Garlow, and this is a phase diagram of the quartic models on the complex sigma plane. So sigma is coefficient at x squared, right? And we have, this was first calculated many years ago by Francois David numerically, right? And we have three phases, and they're distinguished by the equilibrium number of cuts in the equilibrium measure. I will explain immediately. Right, and so there is a one cut region. Now, if we go back to u, right, this is interesting for us. This region is interesting for us because it contains u equals 0. Right, but then there are phase transition to two cut region and to three cut region. Now there are these are in blue. These are critical lines. We will have transition from one phase to another, and we have three critical points, and they are described as Penlever-2. This critical point -2, and these two critical points are Penlever-1. And I will explain just very soon what is the meaning. Right, but the phase regions are described in terms of some equilibrium measures on the complex plane. It is like equilibrium measure is the same as saddle point in asymptotic analysis, but here it is more complicated. It's a measure. And now it's equilibrium measure on the complex plane. And this was analyzed in the work of Arno Kailars and Guillermo Silva. And let me briefly describe the result. And so we consider originally our contour is from -infinity to infinity, but we extend it to what's called admissible contours. And contour gamma is admissible if it goes from -infinity to infinity on the real axis. And it is a finite union of analytic arcs. And now we consider probability measures nu on this contour, on admissible contour, and this is energy functional. Right, this is sort of Coulomb term, right, and this is a term with external field and it is a real part. So now for a fixed contour gamma, we can solve the minimizing problem. It's a very general result in the theory of potential theory, right? And there is a unique minimizing measure. It's called minimizer, right? Which minimizes this functional. So nu here is a probability measure. It can be, and we minimize all probabilities measures on gamma, right? And there again, so very general and very important results about this minimizer. So it's uniquely determined by Euler-Lagrange variational condition, which are written here. So on the support of the equilibrium measure, we have this equation. It is with Lagrange multiplier, and outside we have these inequalities, right? And U here is just logarithmic potential, okay? Right, but next we have to maximize this minimizer over the set of admissible contours. And the main result of Kyle and Silva is that the maximizing contour exists. The equilibrium measure is supported by some set J capital, which is a finite union of analytic arcs. They're usually called cuts. Right, if parameterize the whole contour gamma 0 by some time variable, then we consider, then the cuts are described as intervals from AK to BK on gamma 0. Right, and another analytical property of this max mean measure is that it is a critical trajectory of some quadratic differential where minus r of z d z square, where r of z is a polynomial. So yes, please. Yeah. No, it is not. But okay, but look, suppose that you have asymptotic integral with big parameter you have to evaluate. What you are looking for? Saddle point. And the integral can be over real line, but the saddle point on the complex plane, right? And now you consider contour passing through the saddle point. And instead of saddle point, we have this max mean measure. Yes. Yes. No. But again, so we want to calculate asymptotic. We want to calculate asymptotic of partition function. It is multidimensional integral, and we would like to know asymptotically what is the saddle point in physics. I mean, physicists always talk about saddle point approximation in the random matrices, but saddle point is on the real line. It is just a measure on the real line. It is limiting distribution of eigenvalues or limiting distribution of zeros is the same in fact. Okay, and no, this is the point. So if sigma is real, then the equilibrium measure is on the real line. But if sigma is a complex number, then you have to replace this equilibrium measure on the real line, but some measure on in the complex plane. It's completely not clear by what. And this theory describes you by what is the equilibrium measure for the complex sigma. I'm sorry, yeah. Right. Okay. Right. And the measure, or the set J and the measure max-min measure is unique, but the contour gamma 0 is not unique. You can extend it outside. So the support of equilibrium measure is a collection of analytic arcs, but you have to consider contour from minus infinity to infinity through these arcs. And how you connect, it doesn't matter, basically. Right, and so, but the measure is unique. Okay, right. Now the question is, so this is a sort of abstract theorem that max-min measure exists, but we would like to calculate it. And to calculate it, we have to consider this quadratic differential, and these arcs of the support of equilibrium measure, the trajectories of this quadratic differential, which means that the endpoints are zeros of this function R, and on the support of equilibrium measure, it is this expression is positive, minus R times this squared. Right. Okay. So now to calculate, we use the following very nice equation for R in terms of the resolvent of the measure. And so R and resolvent, they are both on both sides. And so this is not explicit formula, this is an equation. But it's very useful because if you go to infinity, resolvent decays as 1 over z. And basically we have this a polynomial, then something very small at infinity, and then this should be again polynomial. And it's very useful, right? Okay, so let me go. Right. And so for the quartic case, we have this equation. And now we have different possibilities. How many supports of equilibrium measure we can have. It can be 1, 2, or 3, because Q is a polynomial of degree 6. Let us start with 1. Then, considering these asymptotics at infinity, we get equations on the endpoints. So the function I in this case is z square minus b1 square, and plus minus b1 are endpoints of the equilibrium measure, and z0 plus minus z0 are double points of this function R. So right, and we get by considering asymptotics at infinity, we get these two equations on b1 and z0. We solve it, right, and this gives us endpoints and these zeros, right. So this is support of equilibrium measure. Now this is what's called admissible land, where the contour can go to infinity. Right, and this is support of equilibrium measure, and the contour is extended to plus infinity and minus infinity. This for some special point sigma. Okay. Now then we have two-cut equilibrium measure. Then R of z is written this way, and we have two intervals, a1 b1 and minus a1 minus b1. Again, at infinity we get some equations, right, and we can find, right, we can find these endpoints, right. So these are two intervals of the equilibrium measure. There is some density, of course, but it is explicitly given by in terms of endpoints, and this is the contour on the complex plane. Now, in the free-cut case, we have two algebraic equations, but they're not sufficient. And then it is complemented by two real equations, which comes from the condition of which imposed by quadratic differential properties. And now we have three equations on three unknowns. Okay. But there's different. This is algebraic equations, and these are just real equations. And this is an example of free-cut equilibrium measure. And in the one-cut case and two-cut case, equilibrium measure depends analytically on parameter sigma. In the free-cut region, it depends analytically on real part of sigma, imaginary part of sigma, but not on sigma. And so in this phase, we have a property of, okay, it's not analytic in sigma. So it's a phase where we lost analyticity with respect to parameter sigma. And here we, in one cut and two cut regions, we keep it. Okay, so now a very interesting point, how to describe phase transitions in this ensemble. Right, in my relatively old paper with Bertrand Aynard, we proved that sigma equal -2 is the free energy exhibit phase transition of the third order on the real line. Right, and double then with Alexander Ritz, we proved that the critical point, the double scaling limit is described in terms of Penlever 2. And Maurice Deitz and Arno Kailars showed that the critical point 12i and by symmetry -12i, the double scaling limit is Penlever 1. Right. So now the last result is how to describe the critical lines or critical curves separating different phases. Right, and to do this, we consider this change of variables. Beta is a new variable. Sigma is our original variable. And then the claim is that the critical lines are mapped on the critical trajectories, or just trajectories, it's called quadratic, some auxiliary quadratic differential. And it's very powerful property, because then we can use the theory of quadratic differentials to know analytical properties of critical curves. Okay. Right. And so what we proved with Ken McLaughlin and Rusberg Graslow, that the critical curves are described in terms of some auxiliary quadratic differentials. Here I described the critical curve between one cut region and three cut region, but we have another expression for critical curve between two cuts and three cuts. Right, then associated orthogonal polynomials, they admit 1/n square expansion in one cut and two cut phase region. And in three cut, the problem is extremely difficult, and because the partition function can be 0 on a dense set. In a sense, it is probably should be investigated by some asymptotics method of like Kolmogorov-Arnold-Mozart theory, right? When you have small devices, small denominators, but it's not done yet. It's very, very complicated. In original paper of David, he said that free cut region doesn't exist in a sense, because exactly because the partition function is 0 and then set of flow. Right, but mathematically it's very interesting question, very, very difficult. Right, and finally, the free energy admits a topological expansion in the one cut region. Before it was only known for the real line, but it can be extended to the whole one cut region. Right. Finally, a very interesting case is cubic polynomial, because then we're counting graphs of degree 3 or triangulations on the Riemann surface, and phase diagram of the cubic ensemble was described numerically in the paper of François David, and recently we rigorously investigated it with Ahmad Bahromi, Alfred Diagne, and Maxim Yetzov. Okay, thank you.
Thank you. Questions? Sure.
In many two-cut situations, in the normal case, when the polynomial is real,
Yes.
say that it is real and even as a
Yes,
polynomial,
yes.
you have two cuts,
Yes.
AB minus A minus B. And
You have either one cut or two cuts.
yes, let's say that we are in the two-cut phase.
Okay.
Then normally you solve the problem also by using some conformal transformation that brings you to elliptic functions,
Yeah,
Jacobi theta function,
okay.
and so on. But here the things is all carved. It's not clear that there exists. Is
right.
it true or not that it always
It's
exists?
true that. So asymptotics of first orthogonal polynomials recurrence coefficients step by step and is described in terms of Riemann theta functions. And right, and I didn't formulate asymptotics of orthogonal polynomials and recurrence coefficients, but it's in the second term. It's not in the leading term, but in the second term. But it's extremely important for this Riemann-Hilbert approach to analyze the whole asymptotics and the whole series in powers 1 over n square. And then, of course, right, big part of this research is related to investigating of these Riemann theta functions, which involves here. Right. Now, there are some still many problems which are unsolved here. I'm talking mostly in one cut case, you don't have these theta functions. In two cut case and three cut case, you do have these theta functions. And then topological expansion is not like this here, it is much more complicated. And in physics, it was investigated by Bertin Einar, Leonid Chekhov, and many other people. But rigorously, very few results are known, mostly by Gaetan Barreau, right, and some other people, but very few results are known.
Thank you. Any other questions? Yes,
Yeah.
I can see the interest in looking for the phase diagram in the complex parameter space.
Yeah.
But does it have any applications that you?
No, okay, so it has applications in the following sense. So in topological expansion, asymptotic of coefficient somehow involves this critical value you see, and also this three-term K solution of Penlever 1. But why? The answer is the following: if you, that this critical point is the closest to the origin. This critical point with Penlever 1. There are three critical points: Penlever 1, Penlever 1, and Penlever 2. But Penlever 2, if you go to original variables u, is farther away. And so it doesn't affect the asymptotics of Taylor coefficients. But okay, but Penlever 1 does, but it is in the complex plane, so you have to one way or another to investigate continuation of partition function to complex u. Right, if you want to analyze topological expansion. Right, and this is why it's interesting to consider partition function for complex values.
Okay. Any other questions?
Yeah.
If not, let's thank Pavel again.
Thank you.